So welcome to this RISE Learning Machines seminars. RISE is Sweden's research institute with nearly 3,000 people working on a wide array of topics. The computer science department works on applied AI projects for the benefit of society, and we organize the weekly Learning Machines seminars. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. Also, make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce Giulia Fanti, who is an assistant professor at Carnegie Mellon University. She obtained her PhD in EECS from UC Berkeley, and she works on security and privacy and efficiency of distributed systems. The topic today is reducing the communication complexity of federated learning through multistage optimization. So with that, please, Giulia, the floor is yours.
Thank you so much, Olof. Thank you for the kind invitation. It's really a pleasure to be here. Can you all see my screen?
Yes.
Okay, great. Yeah, so today I'm going to talk to you about reducing the complexity, the communication complexity of federated learning. And this was joint work with some fantastic collaborators, Charlie Hu, who's my PhD student and led the project, Kiran Thikumparampil, who was at UIUC and is now at Amazon, and Seung Oh, who's at UW and is actually currently on leave at Google. Okay, so I know this crowd already knows this, but since there may be students in the audience or this talk is going on YouTube, let me start by introducing federated learning. So federated learning is a framework for learning from distributed data. Of course, there's a lot of different variants of federated learning that exist in the literature, but in this talk, we're going to assume a pretty classical federated learning model where we have one central server that's trying to learn a single model from the data of multiple distributed clients. And these clients are directly sharing data with the central server in the form of gradient updates, and can periodically communicate smaller updates that need to be aggregated by the server. Now, one of the main goals of federated learning, as stated in the original paper that introduced the idea, is that of reducing communication costs for clients. So because these clients could be, let's say, mobile devices, for example, or IoT devices, communication is considered to be expensive. And actually, an additional subtlety is that even if communication is not considered to be a bottleneck on its own, if we want to learn a privacy-preserving model, like a differentially private model, the number of rounds or communications with the central server can critically impact our privacy utility guarantees. So there's a few different reasons why one might care about communication complexity in this case, but either way, reducing this communication complexity is going to be the focus of this talk. So a little bit more precisely, in this work, we're interested in a typical federated learning setting where we have N clients that are communicating with a central server. So in particular, we assume that these clients have heterogeneous data. And we'll define exactly what we mean by heterogeneous data in just a second. But for now, you can think of it as each client having data drawn from a different distribution. And these clients are optimizing some objective. So each client has a local objective, F1 through Fn. And the central server is trying to optimize a global objective, which is just going to be the average of all of the local objectives. Now, the clients communicate periodically with the server. And each time they communicate, we call it a round, R. And the question that we care about is how to solve this global optimization with the fewest total number of rounds, R, while accounting for heterogeneity, which I'll use this parameter zeta, or zeta squared, to denote heterogeneity. And I'll define, again, in just a second, precisely what I mean by heterogeneity, because there's a few different definitions that people use. And by the way, if anyone has questions, then feel free to just interrupt me. Okay, So our goal is to solve this federated learning problem in the fewest total rounds R when the data has some heterogeneity, which is captured by the zeta parameter that I showed you on the previous slide. Now, this is a relatively old and well-studied problem. So at a high level, a very common idea for solving it is to exploit local computation. So how do we do that? Well, basically, each client takes several local steps on their local optimization objective before updating the global estimate, before sending their update to the central server. And there's a lot of algorithms for using this locality, including, of course, FedAvg, the classical one. However, the problem is that this doesn't actually work so well on heterogeneous data, at least in theory. Okay, so this picture here is a nice figure from the scaffold paper of Carnegie and co-authors. So here, the setting is that we have two clients, and the orange boxes here are denoting their local optima. And the blue box is denoting the global optimum. So that's what we want the central server to converge to. And so what happens is if the clients take local steps towards their local optima, which are denoted by these blue circles, they slowly make progress towards their local optima. But when they send that progress to the server for averaging, the server starts drifting in a direction that's actually moving away from the global optimum that it's supposed to reach. So this phenomenon is called client drift and is a known problem in heterogeneous federated learning. So the question at a high level that we're trying to answer in this talk is how can we use local computation effectively to theoretically match lower bounds on round complexity? Now, in practice, there has been a lot of success using local steps. Like, for example, scaffolds, the paper that I mentioned on this slide works quite well in practice. But our primary focus in this talk is going to be on trying to understand theoretically what's going on. All right, so I promised you I would define heterogeneity. Let's go ahead and do that before we move on. So there's been a number of definitions of heterogeneity in the literature. We're going to use a fairly common one. And to understand it, let's start with an example. Let's suppose that our client objectives are all linear with different slopes, CI. So this means that our global objective is also going to be linear. So remember, our global objective was the average of all the local objectives. And because these functions are all linear, the global objective is also going to be linear with a slope equal to the average of all of the local slopes. And we'll call that average C bar. Okay. Okay. Now, let's look at the gradients of all of these local objectives. So our gradients are just going to be the slope for each local objective. Similarly, the gradient at the global objective is just going to be this C bar parameter, the average slope across all the clients. Now, our heterogeneity definition is as follows. We take the maximum over all clients, take the maximum over all clients, so I and N, and the supremum over all X in our domain. And we take the difference between the gradient evaluated at that client and at that point, that's the second term, and the global gradient evaluated at that point. Okay, so we're trying to find at what point in our domain and across all of our clients do we deviate the most in gradient from the true global gradient. So for this particular example, our global gradient would just be the C bar parameter. It's the same everywhere for all X, so we can ignore this sup term. And for the individual clients, it'll be the CI. So our heterogeneity parameter here reduces to taking the maximum over all clients, the difference between C bar and CI. Okay. So you can think of this as like a worst case heterogeneity definition. Now, to understand what is the problem with heterogeneity, I want to walk through a toy example just to build some intuition. So again, let's suppose that we have two clients And let's suppose that each of them has a quadratic objective. Call them F1 and F2. Okay, so F1 is this expression on the left and is denoted by the green dotted line here. And F2 is the expression on the right and is denoted by the red dotted line. And our global objective is going to be the average of these two, which we denote by this blue solid line. This is the one we're trying to optimize. Now, note that the global optimum for this problem is x star equal to -1/3. Okay, that's the minimum of the blue curve. However, if we take the optima of these local objectives and just average their location, we get 0, okay, which is not correct. So the red curve is optimized at -1, the blue curve is optimized at 1. So if we just average those locations, we get 0. So that doesn't solve our problem. So we can't just optimize each of the local optima and then average. We have to do something else. And this is where various federated learning algorithms come in. Now, to solve this problem, there are two main approaches or classes of approaches in the literature. The first is to use local methods like FedAvg. So in a local method, we do something like the following. We start with some initialization point. Okay, so in each round, the server sends the current iterate to the clients. So let's say our initialization point is something like -3.5, okay, for all clients. Then each client is going to take k local steps over their local objective. So in this case, we'll take 1, 2, 3, 4 local steps on each local objective, and then return the resulting xi, the resulting iterate. Okay, and the server can update these iterates by average. Okay. So each communication round in this case is spent by having the server collect these final client iterates and average them, and then we resume this loop in the next round. Okay, so what's wrong with FedAvg? Well, let's try to think about why this might not perform well. So in this figure, I'm showing you the objective functions in the top figure, which is what we saw in the previous slide. And in the bottom figure, I'm showing you the gradients of the local objectives and the global objective. And the thing that I want you to notice is that we have these yellow regions on the outside and a gray region in the inside. And in these yellow regions, we have that the signs of the gradients agree for all of our local clients. So in particular, if we look at this yellow region to the left of -1, we can see that both the gradient of F1 and of F2 are both negative in sign. Okay? And in the region above 1, they're both positive in sign. In contrast, in this middle gray region, they have differing signs. Okay? So one of the clients thinks the gradient is positive, the other thinks it's negative. So what this means is that inside the middle region, inside this gray region, there's always at least one client's update that is dragging the server iterates away from the global optimum because it's pointing in a different direction. Okay. So intuitively, the problem with local methods is that your objective value decrease may slow near the optimum because you have disagreement among different clients. And this is kind of inherent to heterogeneity. Now, formally, this kind of intuition leads to the following convergence rate, which was shown by Woodworth and collaborators in 2020. So here I'm showing you the difference between our F, our global objective, evaluated on X hat, which is our current iterate after R rounds of communication, minus the true optimum, so F of X star. So this is our suboptimality gap here on the left. And on the right here, we have zeta squared. This is our gradient heterogeneity parameter that I defined earlier. We have mu, which is a strong convexity parameter. So this result is assuming strong convexity, and I'll use strong convexity in several of the results in this talk, but our results do extend to other settings as well. R here is our number of communication rounds that we've executed so far, and kappa is our condition number. So we're also assuming some smoothness on the function. Okay, so I want to point out two things about this convergence rate. So the first is that it scales quadratically in the heterogeneity zeta. Okay, so what this means is that as our heterogeneity gets smaller, or our problem gets more homogeneous, we can actually converge faster. The second thing I want to, so that's a good thing. That's kind of intuitively what we want. We would like to be able to take advantage of small heterogeneity. The second thing I want to observe is that this quantity is decaying quadratically in R. Okay? And this is actually fairly slow, or at least what we would like is for this to decay exponentially fast in R. Okay? So FedAvg is able to take advantage of heterogeneity, of low heterogeneity. Sorry, there's a dog in the office. Is able to take advantage of low heterogeneity, but its convergence rate is fairly slow in terms of number of rounds. Okay, so let's look at a different class of approaches, which are called global methods. So this other approach does the following. Here, in every communication round, each client will communicate one stochastic gradient update, okay, which gets averaged at the server. So the way that we do this to ensure a fair comparison is that each client will take the current iterate x, and it will average k stochastic gradients computed over fi, okay, over its local objective. And it returns the resulting xi, the resulting update to the server. So stochastic gradient descent, or mini-batch stochastic gradient descent, is an example of such an approach, as are accelerated variants of SGD. Okay, so just to show an example of this, basically in each communication round, the server is averaging the updates from all of the clients. So after 4 steps of optimization, we end up looking something like this. Okay. So what's wrong with SGD? Well, the main problem with this approach is that SGD communicates on every update. Okay, so it doesn't make use of local computation at all. And what this means intuitively is that it cannot take advantage of client similarity. Or in other words, it can't take advantage of the fact that if clients have kind of similar objectives in a particular region, like we saw earlier, the area where all of the gradients were pointing in the same direction, SGD is not able to exploit that fact. And this observation shows up in the convergence rates for SGD as well, which were shown in the same paper. So here again, we have the suboptimality gap on the left. And here on the right, we have the following expression. So this delta is our initial suboptimality gap. Here again, R is our number of communication rounds, and kappa is our condition number. So here again, I'd like to highlight 2 key points about this expression. The first is that it doesn't depend at all on heterogeneity zeta. So intuitively, this means it can't possibly take advantage of the low heterogeneity setting because it has to account even for the highest heterogeneity possible. And so this is kind of a downside. But on the other hand, the good thing about this expression is that it's decaying exponentially fast in R, which remember is what we wanted from the previous slide. And in fact, this convergence rate can be sped up slightly with acceleration. And we can see that instead of having this expression on top, we can get a square root on the kappa. But even with this accelerated version of SGD, we still cannot take advantage of heterogeneity. So if we compare these 2 classes of algorithms, and specifically FedAvg and SGD, we get that unless the heterogeneity is really tiny, which is covered by this expression, SGD actually does better than FedAvg. Okay. So let's take a second to parse this. So we need our gradient heterogeneity to be less than mu, our condition number, times epsilon, which can be really tiny in practice. So we really need our heterogeneity to be quite small in order for FedAvg to theoretically outperform SGD. So this is a little disappointing because it kind of means we aren't really getting theoretical benefit from FedAvg, at least in terms of communicate or round complexity. All right, so this intuition holds more generally. So across a range of settings, so all of the results that I showed you earlier are for the strongly convex setting. But even if we look at the convex setting and even the non-convex setting, there have been some results, mainly under the PL assumption. We don't really know, there's two problems that I want to highlight. The first is that we don't really know what to do in the intermediate heterogeneity regime. It's clear right now that if you have very low heterogeneity, you should use FedAvg or some kind of local method. It can speed up your convergence both theoretically and in practice. It's also clear that at very high heterogeneity, you should be using SGD or some kind of global method. And this has been shown to be order optimal. But in the intermediate setting, it's not clear what to do. And kind of more generally, the problem is that existing optimization algorithms cannot achieve both fast convergence in R, where by fast I mean exponentially fast, and second, flexible dependency on heterogeneity zeta. Okay. So in this work, we aimed to address these issues by designing a federated chaining framework, which we call FedChain. So this is aiming to provide a single framework across different heterogeneity settings, which achieves near optimal communication complexity up to exponentially vanishing terms across various settings. So we will show near optimality for mu strongly convex problems. For general convex problems, we get near optimal convergence rates at high heterogeneity. And for mu PL non-convex problems, we get near optimal convergence rates up to factors of the condition number. So I'll make those statements more precise in a little bit. And this, the main contribution here, I guess, is that this is the first approach to theoretically improve on both FedAvg and accelerated SGD in different heterogeneity regimes. So, all right, so what is FedChain? What is this federated chaining framework? It's actually extremely simple. The idea is that we start by using the knowledge that we're going to run for a total number of rounds R. And we're going to split our optimization algorithm into two phases. In the first phase, we will use a local algorithm. Okay? And this local algorithm, like FedAvg, scaffold, FedProx, will run for R over 2 rounds. Then in the second phase, we're going to switch over to a different optimization algorithm, which is a global algorithm. So here again, you can use whatever global algorithm you like. You could use SGD, accelerated SGD, Saga, you name it. Now, there's an additional subtlety here, which is at the end of the local algorithm, we take a minimum between the output of the local algorithm, which I'll call x1/2, and the initial point, x0. And the reason for this is that in some cases, local algorithms can actually cause your global iterate to move farther away from the optimum than the initial point. So this minimum is basically just allowing us to take the smaller or the better of the 2 points. And we feed that as input to the global algorithm for the second phase of FedChain. And then the final estimate is x hat. This is the output of these 2 algorithms. Okay, so that's FedChain, very simple. And in fact, the proof is also extremely simple. So I'm going to show you the convergence rate for FedChain instantiated with FedAvg for the local algorithm and accelerated SGD for the global algorithm in the mu strongly convex and beta smooth setting. Okay. And I'm going to use this notation generally of algorithm 1, arrow, algorithm 2 to denote that the first one is a local algorithm and the second one is a global algorithm in FedChain. So we start with this known convergence result for FedAvg, which I showed you in an earlier slide. And as well as the known convergence rates for accelerated SGD, which I also showed you on an earlier slide. And the thing that I want to observe here is that this leading term in front of the accelerated SGD expression is delta, is the initial suboptimality gap. Now, we can actually instantiate that by running FedAvg for R/2 rounds and getting the corresponding convergence guarantee, and basically just plugging that in to the delta term for the second algorithm, for the global accelerated SGD algorithm. Right? So our final convergence guarantee for FedAvg to ASGD looks like the following. So here we have out front, we now have a scaling in terms of zeta. So we have this zeta squared term out front. And we also have an exponentially decaying term in R. And here notice we have this R/2 because we ran our algorithm, our local algorithm for R/2 rounds. Okay. So here I'm ignoring the effect of the min from the previous slide, the minimum of the output of the local algorithm and the initial point. But I'll show you the effect of this on the following slide. Now, it turns out that this convergence rate for FedAvg to ASGD pretty closely matches a lower bound that we can show for the same setting. And the lower bound states that for any first order federated optimization algorithm, and I'll go over the conditions of this lower bound in the next slide, there exists a strongly convex set of objective functions such that after R rounds, our suboptimality gap scales at least as this expression. Okay, so here we have a min of a term that depends on zeta squared, our heterogeneity, and the initial suboptimality, and an exponentially decaying term. Now here I'm going to reproduce the upper bound that I showed you on the previous slide. And the thing that I want to observe is that this exponential term matches up to a factor of 2 in the R. And so we get the same or similar exponential decay in terms of the number of rounds R. And out front, we have this min term, which is coming from that minimum block in the definition of the FedChain framework. And it takes the minimum of a term that depends on our heterogeneity and our initial suboptimality. Okay. So I told you I would give you a few more details on how we actually show this lower bound and what assumptions we make. So we make a couple of assumptions on, first of all, the algorithm class, the class of first order algorithms that we consider. And the proof roughly follows the structure of the work of Woodworth, Patel, and Srebro in a paper called Mini Batch versus Local SGD for Heterogeneous Distributed Learning. And this proof in turn is inspired by the classical proofs of Nesterov. So this may look kind of similar, may look kind of familiar to you. But we make two assumptions on the class of algorithms that we are considering. The first is that it is what we call distributed zero respective. So what does that mean? It means that a current iterate can have a non-zero value at a coordinate I if and only if the algorithm has seen a non-zero entry in a gradient at that coordinate from a previous round iterate or client. So what is that saying? In the words of Woodworth and co-authors, this is basically just saying that your algorithm is not wildly guessing, okay? And this same type of construction was used also in the classical proofs of Nesterov. The second assumption is that the class of algorithms is distributed distance conserving. Now, this is a notion that we introduced in this work, and it means that iterates do not move too far away from the global optimum, more than the initial distance to optimum times a log factor. Okay, so let me illustrate this with an example. Let's suppose, again, we have two clients, client 1 and client 2, and their local optima are x1 star and x2 star. And let's suppose that we initialize our problem at this point x init, and our global optimum is this x star. So the first thing we're going to do is compute the distances between our initialization point and our local and global optima. Okay, so we'll call D1 the distance between our initialization and x1 star, and D init is the distance to the global optima. Next, we're going to draw a ball, which is centered at x star, at the true optimum. And the radius of this ball is going to be equal to some constant factor multiplying the sum of the distance from x init to each of the local optima and to the global optima. And we require that this leading c be no more than polylogarithmic in other problem parameters, in all of the problem parameters. So we call this ball AC, and AC is basically the range of possible values that the iterate can take. So we want to ensure that if you start at the point x init, with high probability, all of your iterates are going to remain within the ball AC. Okay, so that's what we mean by distributed distance conserving. Now, based on this notion of distributed distance conserving, we make another assumption on the function class, so the class of objectives that we are considering. And in particular, we call this condition zeta C heterogeneous. So this is basically just slightly modifying our heterogeneity definition from before. So if you notice, this looks identical to our heterogeneity definition from before, except now when we take the supremum, previously it was over all x in the domain, but now we're taking it over all x in this ball AC. Okay, so we only worry about the heterogeneity within this ball. Okay. So these are the assumptions we make, and after that, the proof follows kind of a traditional structure for these kinds of convergence lower bounds. All right. So so up to now, I've shown you that Fed chain, an instantiation of Fed chain, can come pretty close to lower bounds on the convergence rate for strongly convex and smooth problems. Now, up to now, I've also been making some simplifying assumptions. And one of these is that we have full client participation, which means that in every round of communication, every one of the clients is participating in the protocol. Now, of course, this is not necessarily a very realistic assumption, especially in client level federated learning, where you could have billions of devices that are participating. So in reality, we often operate in settings where clients are sampled in each round. So only a subset of clients participate in each round. So we extended our analysis to this setting, to the setting where in each round, we sample S out of N clients uniformly at random. And unfortunately, to our disappointment, when we did this, we found this basically the same expression from before, plus this nasty term that depends on the heterogeneous client sampling variance. Okay. And the reason I call this term nasty is because it is basically dominating the earlier term, which means that we don't get the nice properties that we had previously asked for from our framework. Okay. So in particular, this exponential decay in R goes away. So why is this happening? Well, intuitively, the problem is that cross-client sampling variance behaves kind of like sampling variance in finite sum convex optimization. So if you think of the classical convex optimization problem where you have a finite sum objective, and in each iteration, you're randomly sampling some subset of those objectives to participate, you get a similar a similar term in your convergence rates, and we'll see that in just a second. So inspired by the literature in finite sum convex optimization, we tried a solution that is similar to what has been done in that domain. In particular, we tried server-side variance reduction in the global algorithm. And in fact, by doing this, you can actually get rid of some of these pesky terms that I showed you earlier. So here on the bottom, I'm showing you a convergence rate for FedAvg for the local algorithm and SSNM for the global algorithm. Now, SSNM is an accelerated version of Saga, which is a variance reduction algorithm. So this global algorithm, the second algorithm, is an accelerated variance reduction algorithm. And what we found is that by doing this, you can get an expression that moves the sampling terms from an additive term into the exponential term. Okay. Okay. So to understand what's going on under sampling, it can be, I think it's kind of helpful to see directly the parallels between the two settings, the centralized finite sum convex optimization setting and the federated learning setting that we're talking about here. So in the centralized setting, our sampling procedure is basically sampling S data elements out of N. Whereas in the federated learning setting, we're sampling S clients out of N. Now, in the centralized setting, we have an assumption that the sampling variance is bounded by some term sigma squared. So in particular, you have this expression that you'll notice looks a lot like our definition of heterogeneity. Okay. And finally, we get that the convergence of accelerated stochastic gradient descent in the centralized setting over R iterations looks very similar to the convergence of accelerated stochastic gradient descent over R rounds in the federated setting. So here we can see the convergence rates for both of these algorithms, and we see that they're basically identical, except for this sigma squared term in the centralized setting and the zeta squared term in the federated setting. So basically the sampling variance from the centralized setting is playing the same role as heterogeneity does in the federated setting when you're sampling over clients. So this kind of helps to explain why variance reduction should help. And indeed, if we include these sampling terms into our upper bounds, we can get results again in the mu strongly convex setting, the convex setting, and the mu PL non-convex setting. So this table is a little bit hairy, so I'm not going to parse all of it, but I wanted to point out a couple of things. So the first is that in all three of these settings, the best known algorithm to date is some variant of FedChain. So in particular, it's the ones that are listed here, the instantiation that we've listed here. The second thing I want to observe is that we get near optimal convergence in the mu strongly convex setting. So here we're off by this factor of root S over N. And then there's some factors of the condition number out front and mu. In the mu PL setting, we also get close to the lower bound up to factors of kappa. So notice here in the lower bound, we have a root kappa, whereas in the upper bound, we only decay as 1 over kappa in the exponential term. And the other observation that I want to make is in the general convex setting, there is a gap between the upper bound and the lower bound. But this is the tightest convergence rate with sampling to date for federated learning algorithm. So this is kind of how FedChain compares to existing lower bounds and prior work. And I also want to mention here that we've set the smoothness in this table, beta, equal to the initial suboptimality gap, D, which we set equal to 1, really just to reduce the amount of notation in this table, which is already substantial. Okay, so I've talked to you about kind of the theoretical benefits of FedChain. I want to also show you some empirical results. And one of the challenges in trying to evaluate FedChain and basically heterogeneous federated learning in general is how to vary heterogeneity. So in this case, we came up with something based on the MNIST data set. Well, you can do this with any data set, of course. And what we did was the following. We split our initial data set into clients. For MNIST, we split it based on digits. Okay, so for example, each digit would correspond to one client. Then we would take, let's say, 30% of the samples from each digit, and we would shuffle all of those samples and partition them across clients. Okay, and we call this the 30% homogeneous setting because 30% of the data is uniformly shuffled across all of the clients, whereas the rest of the data from each client is still heterogeneous. Okay. So intuitively, the more we shuffle, the closer we get to a fully homogeneous data set. Then we ran this optimization on logistic regression, regularized so that the objective is strongly convex. And in this plot, I'm showing you the gradient norm as a function of the number of optimization rounds on the horizontal axis. And so here we're showing 3 baselines. The blue curve is accelerated SGD, which is a global method. Scaffold is a local method. It's this orange dotted curve. And then the green curve is FedChain instantiated with scaffold for the local method and SGD for the global method. And this red line here shows where we transition from scaffold to SGD. And these green points show where we do step size decay. So I have some other plots where we show step size decay for all of the baselines. It gets a little bit hairy. But in general, the observation that I want to make is that by transitioning from a global to a local algorithm, you can get some gains in terms of the gradient norm, in terms of the convergence rate, particularly on strongly convex problems. We also observed gains in the non-convex setting, though they were not as significant, I would say. So we ran experiments on the eMNIST handwritten digit data set, and we partitioned these by author. So there were 3,400 clients. And we learned a CNN for digit classification. So this is a standard benchmark from the Federated Learning Test Suite by Reddy and Charles. And what we found is that by using FedChain, so here the first 3 rows are showing our baselines, our global methods and local methods. And by instead using chained methods, we're able to get a gain in test accuracy of between 2 and 7%. So here in this setting, we ran this for 500 communication rounds and had 20 local client epochs and a sampling factor of 10. Okay. Oh, and one kind of intuitive, or one point that I want to mention is that in the we noticed significant differences in when you should switch from the local method to the global method. So notice on this previous plot, we switched pretty early. And in our experiments, we treated this switching time as a hyperparameter to be tuned. So in theory, it doesn't matter. In practice, we treat it as a hyperparameter. And so for convex problems, we noticed that you should switch pretty early. You should only do local methods for a few steps, and then you transition to global pretty quickly. In non-convex problems, we noticed the opposite. You should actually use local methods for most of the optimization, But then if you switch to global towards the end, you get another little bump in test accuracy. So this observation, this empirical observation, raises kind of an interesting question, which is how many local rounds do we actually need? So in the theory, when I presented FedChain to you initially, I said that we were going to spend half of our rounds on the local method and half of our rounds on the global method. In reality, the theory works out as long as you have a constant fraction of rounds in the local and a constant fraction of rounds in the global, and it doesn't matter what that fraction is, as long as it's constant. And in the empirical setting, we have yet another story, which is what I just told you. So in the convex setting, we want to switch pretty early in the optimization, and in the non-convex setting, we switch pretty late. So can we get some guidance on when exactly you should switch? And to try to understand this, we ran an extreme example, which is where we used only one local round. Okay. So here, I'm going to be using a variant of FedChain, which I'll denote by 1x to y, which means that you run local algorithm x for just one round, and then the rest of your r-1 rounds are run using global algorithm y. And so in these plots, I'm again showing you on the horizontal axis number of rounds, and on the vertical axis our gradient norm squared. And basically these curves with the little stars on them are examples of one FedChain. So like this gray curve is one round of scaffold, which is run basically to convergence, and then we transition to the global accelerated stochastic gradient descent. And we find that by using just this one round of local optimization, you can get much faster convergence than by using our other baselines, which suggests that maybe you only need one round of local optimization. Now, we don't fully understand why this is happening. We're still trying to figure this out, but I can give you some preliminary results, some preliminary theoretical justification for why this might be occurring. And to do this, we introduce a new definition of heterogeneity, which is shown here. So recall that our old definition was evaluating how much the global gradient could differ from local gradients. Our new definition of heterogeneity is instead going to look at the local optimal point for each client. So that's xi star. And it's going to look at how far away is f of xi star from the global optimum. So intuitively, it's trying to capture which of the clients is guessing the global optimum best and how far from optimal are they. So I'm just going to step through a quick example to illustrate this. Okay, so we're going to go back to our old friend, the toy example from before. So in this case, we know that x2 star is -1, okay, is the optimum of the red dotted function. And we evaluate the global objective at f of x2 star. Then we take x1 star and evaluate it on the global objective. And we check which one of these is closest to the true global optimum, f of x star. Okay, so in this case, f of x2 star is lower. So that's going to be our the outcome of this optimization. And so in this case, delta het, our new heterogeneity, is going to be f of x2 star minus f of x star. So this is our new heterogeneity definition. And under this heterogeneity definition, we analyzed a new algorithm, which I'll call one oracle to ASG. So the algorithm here is that each client optimizes their local objective to completion. So the output is the true xi star. And it returns that xi star to the server. And this is the main difference between one oracle ASG and one FedAvg ASG. In this case, in the oracle case, we're getting the exact optimum, Whereas in the FedAvg case, we can only optimize it for, let's say, k local steps. Right? So we provide the central server with these Oracle solutions from each local client, and then we run accelerated stochastic gradient descent to convergence, initialized at the best of the local optimum. So again, if we go back to the strongly convex beta smooth setting, we can get a convergence rate that looks like this. So here, this delta het is the new heterogeneity parameter that I defined for you. R is our total communication rounds, and kappa is our condition. Okay, so we see that we get both of the properties we wanted. We have a dependence on the heterogeneity, and we also get exponential decay in R. And in fact, if we compare this to another lower bound, we see again that, the proof here is very similar to the proof from before. So again, we use known convergence rates for accelerated stochastic gradient descent. And we know that the local step, the Oracle step, gives us the true optimum, the true best local optimum, which we'll call X het star. So what we do is initialize the global phase, the accelerated stochastic gradient descent, with X het star, which gives us a suboptimality gap that is exactly equal to our heterogeneity definition, our new one. So, so the proof again is dead simple, and gives us both of the properties that we want. And we noticed that, again, we can show a lower bound for a similar setting as before. That looks like this. And if we compare this to the convergence rates for one Oracle ASG, we get that these are very close to one another. So there's two things to observe here. Recall that earlier in our upper bounds, we had this factor of R over 2. In this expression, we've gotten rid of that R over 2. The exponential decays are exactly the same, including in factors of kappa. And the other observation is that out front, these two expressions match one another better, especially if your initial suboptimality gap is large. So, okay, and the other thing that I wanted to mention is that you may have noticed in our earlier convergence results that we had these kind of pesky O tildes, which were hiding logarithmic factors in other problem parameters. And under this simplified analysis framework, you can get rid of those O tildes. These are big O convergence rates. We believe that some version of these results should also hold in the general convex setting, but we don't have those results yet. So that wraps up what I wanted to talk about today. So to summarize, Fed chain achieves near optimal convergence rates in the strongly convex setting. It is the first framework to uniformly match or improve on FedAvg and ASG across all heterogeneity regimes. And it can also be applied to other settings like the strongly or general convex setting, PL non-convex. And it can handle both full and sampled participation from clients. However, it leaves a lot of open questions, I think, one of which is this issue of how many local steps do you actually need? I think that's a really important question that we don't have a good handle on yet. And it would be great if someone else figures it out as well. And additionally, I think you can view the Fed chain framework as a coarse-grained version of multi-stage optimization. But actually doing multi-stage optimization in the federated setting is still an open problem. People haven't figured it out. So I think analyzing decaying step sizes in the federated setting would be really interesting, especially because we've observed empirically across many, many papers that it's beneficial. So with that, thank you so much for your time, and I'll be happy to take any questions.
Thank you for the talk, Giulia. Do we have some questions from the audience? Perhaps I can start. I'm a bit curious about the server-side variance reduction that you talked about. Can you say some intuition about how does this affect the learning?
So there's kind of two ways in which one can answer that. I talked in the presentation mainly about the theoretical component, and so the point is that it gets rid of that. Let me try to find it 1 second. Okay, here.
Yes. So the question is more like, do you also remove? It sounds like you're removing information. So can we still converge as well?
We do still converge, but okay, in theory we do still converge, but in practice what we found is that this actually doesn't work as well as one would like. So I think, and in fact, variance reduction has been proposed in other papers as well, and we've kind of been struggling with, like, is it actually a good idea? And I don't think we are internally convinced that it is. Yeah, so this is actually, maybe I should have mentioned this on the last slide. I also think that this is an interesting question, whether variance reduction actually does help in federated learning. And I'm not personally convinced one way or the other.
Okay, so in the experimental results that you showed, it's not included there.
It's not included. We did this. That's not because we did these results a little bit. Added these theoretical results a little bit later, and I think this was just a matter. I believe we had some empirical results on the variance reduction, but yeah, the settings where FedChain worked best were without variance reduction.
Okay, thank you.
So I might have a question here on slide 25. You have some experiments with MNIST logistic. I don't understand. You have scaffold and then you have scaffold plus SGD, but shouldn't they be the same in the first iterations here then?
Yes. Sorry. This is because the scaffold SGD curve is including the step size decay optimization. So this isn't entirely a fair comparison. I think I might have. Oh no. Yeah, I'm sorry. My cloud storage was giving me trouble yesterday, so I don't actually have the backup slide that I wanted to show. But we do have plots where we did step size decay for all of the baselines, and it just looked a little bit messier, which is why this is the plot that I'm showing. But you're right that if you apply exactly the same hyperparameter optimization, scaffold and scaffold to SGD look the same up to the point where you switch.
Okay.
Yeah.
Good. Thanks.
Do we have some more questions for Giulia? Sort of what will be the next steps in this research direction?
That's a good question. I think one of the pieces of feedback that we've been getting from industry is that heterogeneity isn't maybe the most important issue for them. So I think we're actually moving on or looking at other directions entirely. Okay, there's 2 points, I think. One is that heterogeneity is maybe not as big of a problem as it might seem from the academic literature. And the other is that communication complexity also may not be as big of a problem unless you're taking into account privacy budgets. So I mentioned this at the beginning of the talk, but if you're trying to learn a differentially private model, you have a privacy budget, and that constrains how many rounds of optimization you can do. So the communication cost may not be a problem of its own right, but only in conjunction with privacy constraints. And so like potentially analyzing those or trying to understand the interaction between privacy and optimization, I think could be an interesting direction as well.
Yeah, sounds interesting. Right. So if we have no final questions, then we're ending on the spot of 4 o'clock here in Europe, at least. It's 10 o'clock where you are. So welcome back, everybody. Next week, we'll have Lena Voita, who is at Facebook AI Research. She'll be talking about a journey on interpretability methods in NLP, inside, out, and back. So that will be next week. Thank you again, Giulia, for the talk.
Thank you. Thank you all.
Bye-bye.